Hey everybody, it's Mr. Cadell. We are almost done with cellular respiration. Today we'll finish. I wrote myself a note. It only takes 15 minutes. We'll see about that because I'm kind of long-winded. You haven't noticed that by now, have you? Let's orient ourselves. So here we are at 9.5. Here's a picture that I'm going to show you right now. Make sure to get this picture out. It has both of the two processes of fermentation that are up there on the board, or you can just go to your textbook. We'll talk a little bit about this picture. I'll show you this picture, and then we'll go from there. Let me give you some background as far as what I want you to do. With respect to 9.5, I will tell you what you need to know right now. Again, no trickery with respect to anaerobic fermentation of the pyruvate, which is the compound that comes out of glycolysis. Make sure that you study these figures, 9.17 and 9.18, but I really like 9.6, the reading that's in there. Don't read page 182, but I like page 180 and 181 in the 10th edition. That would just be the first two pages of that section. The literature doesn't change very much from edition to edition. Well, like normal, let's start with a movie.
Oh, sugar, sugar, you are my favorite fuel from the blood-borne substrate pool. Glucose, I'm a saccharide sugar. You're sweeter than a woman's kiss, 'cause I need you for glycolysis. I just can't believe the way my muscles take you for you.
Couldn't you just listen to it all night? All right, here's a little video from the book's publisher.
Mountain biker heads up the trail. The breakfast he ate this morning is being burned to power his bike ride. His breathing rate increases as his leg muscles demand more oxygen to burn more fuel. Let's zoom down to where this fuel is burned, our cells. Here, the blood vessel on the left delivers fuel and oxygen to a single muscle cell. In cellular respiration, energy and fuel is converted to ATP, shown here as starbursts. Most ATP is made in the cell's mitochondria. ATP powers the work of the cell, such as contraction. Let's take a closer look at how ATP is produced from a molecule of glucose, our fuel. Only the carbon skeleton is shown to keep things simple. The first step is called glycolysis, and it takes place outside the mitochondria. To begin the process, some energy has to be invested. Next, the molecule is split in half. Now, the molecule NAD+, an electron carrier, picks up electrons and hydrogen atoms from the carbon molecule, becoming NADH. Keep track of the electron carriers. They play an important role by transporting electrons to reactions in the mitochondria. In the final steps of glycolysis, some ATP is produced, but not much. For every glucose molecule, only 2 net ATPs are produced outside the mitochondria. However, glycolysis has produced pyruvic acid, which still has a lot of energy available. Let's follow this pyruvic acid molecule into a mitochondria to see where most of the energy is extracted. As the molecule enters the mitochondria, one carbon is removed, forming carbon dioxide as a byproduct. Electrons are stripped, forming NADH. Coenzyme A attaches to the 2-carbon fragment, forming acetyl-CoA. Coenzyme A is removed, and the remaining 2-carbon skeleton is attached to an existing 4-carbon molecule that serves as the starting point for the citric acid cycle. The new 6-carbon chain is partially broken down, releasing carbon dioxide. Several electrons are captured by electron carriers, and more carbon dioxide is released. The carbon dioxide that you exhale comes from the reactions of cellular respiration. 2 ATPs are produced by the citric acid cycle for each molecule of glucose. At this point, only a small number of ATPs have been produced. However, more energy is available in the electrons that are being transported by electron carriers. While the citric acid cycle starts another round, let's follow an electron carrier to the next step in the process. Electron carriers such as NADH deliver their electrons to an electron transport chain embedded in the inner membrane of the mitochondria. The chain consists of a series of electron carriers, most of which are proteins that exist in large complexes. Electrons are transferred from one electron carrier to the next in the electron transport chain. Let's take a closer look at the path electrons take through the chain. As electrons move along each step of the chain, they give up a bit of energy. The oxygen you breathe pulls electrons from the transport chain, and water is formed as a byproduct. The energy released by electrons is used to pump hydrogen ions, the blue balls, across the inner membrane of the mitochondria, creating an area of high hydrogen ion concentration. Hydrogen ions flow back across the membrane through a turbine. Much like water through a dam, the flow of hydrogen ions spins the turbine, which activates the production of ATP. These spinning turbines in your cells produce most of the ATP that is generated from the food you eat. The process you've just observed, cellular respiration, generates 10 million ATPs per second in just one cell. That ATP can power a biker up the trail, or it can power your brain cells as you learn challenging biology topics.
All right. If you need help with this chapter, again, talk to me, spend some time with it, struggle a little, work with a friend, look at all these videos. There's a ton of resources here to help you, but it's not easy. I will acknowledge that. To me, it's one of the hardest things that we will learn this year, my opinion. Before we go any further, what I would like you to do is to hold your breath. So I will keep time. We're going to start in 5 seconds. Okay, go. We're at 30 seconds. Forty seconds. 50 seconds. 'And there's a minute. Good job. If you're still holding your breath, that's good. You can press pause if you'd like. I'm going to move on. I hope that you think while you're holding your breath, obviously it's an exercise, but why must we breathe? I want you to press pause and I want you to say it out loud. Why do we breathe? I mean, think about it. When you run around the track and you're moving a lot and you're contracting your muscles and the ATP is being generated at a high rate, you breathe more rapidly. Did you ever wonder why that is versus when you're just sitting in a classroom? And of course, the answer is this, and I've asked this on a test before as a test question. Remember, the reason why we breathe is to bring oxygen into our body, into the bloodstream, diffuse throughout the blood to different cells, diffuse into the mitochondria. The reason why we want oxygen there is because as those protons go shooting through that ATP synthase enzyme and spin it to make ATP, we have to maintain that gradient of a high concentration to low concentration. If in fact, let's say you hold your breath and there's no oxygen there to take those protons away by binding with the electrons and protons to make hydrogen atoms and then take it away to make water, and I've shown you that on the board a couple times. If you don't have that reduction of concentration of these protons, there will be no driving force for them to go through this ATP synthase enzyme through diffusion, and there'll be no rotation and no ATP made. This is why people die or get Dane damage, is if you don't have air going to your brain for, however many minutes, 8, 9 minutes, 10 minutes, whatever, you start to kill cells. Like literally no ATP is made and they will start to die. There are drugs that work on the electron transport chain also, like cyanide, I know, inhibits one of those proteins in the chain, so it can't, be reduced and then oxidize and move those electrons down the chain. And that's another way that you stop ATP production. Rotenone is another, it's like an insect killer. That also works on the proteins in the electron transport chain by stopping them. Anyway. So I want you to look at this picture, and I want you to appreciate glycolysis. For about 800 million years on this planet, there was life, single-celled life, in the primordial soup of our ancient oceans, and there was no oxygen in the atmosphere. And so these individuals evolved a way to break down glucose into pyruvate. A little bit of ATP was made, but that was it. And that's why bacteria, or these single-celled organisms that only do glycolysis, why they've never evolved to be able to ski down mountains or read great literature or program computers. They just don't have enough ATP to evolve over billions of years, different systems and cell formations that will allow them to do that. It's just inefficient. Breaking down glucose and getting 2 ATP is way less efficient, 17 times less efficient than getting 34 ATP out of one glucose molecule. The question becomes then, do we ever only do glycolysis? And the answer, of course, is yes. You only do glycolysis if you can't deliver oxygen enough. And when might that happen? Well, maybe when you're holding your breath, or maybe when you're working out. Is this a bad thing? Well, you can imagine how inefficient it is with breaking down of the food. But I'm going to argue that in training anyway, it's actually a good thing. So fermentation and anaerobic respiration enable cells to produce ATP without the use of oxygen. It's not enough for us, but it is enough for some organisms to be able to survive this way. Like yeast, for instance. Yeast can survive either anaerobically, no oxygen, by just doing glycolysis, although it won't thrive or live as long as if it does have oxygen, and it can also do cellular respiration. It's kind of cool how it has evolved the ability to do both of these things and survive. We can do fermentation, but we just can't survive very long while doing it. So I want you to look at this picture. This is lactic acid fermentation, and this is what we do when we're not delivering enough oxygen in order to tell that one carrier protein on the side of the mitochondria that yes, glycolysis happened, there is enough oxygen. Let's get this pyruvate into the matrix of the mitochondria to do the link reaction in the citric acid cycle. If you notice across the top here, you see that glucose undergoes glycolysis, 2 ATPs are made, 2 NADs are reduced. We have pyruvate at the end on the right side there. What happens then is the pyruvate undergoes this transformation where it actually takes those 2 hydrogens back, and you can see something is formed. It's called lactate. Lactate has another name, lactic acid, and it literally is an acid. There are many organisms, like some bacteria, that just do this. They create lactic acid all the time. We use these bacteria to our advantage. They help us make pickles, sauerkraut, cheese, yogurt, things like that. We make lactic acid sometimes, and it's kind of a dangerous situation because you literally are making acid. Have you ever worked out really hard and then been super sore the next day? Now, yes, maybe you had some micro tears in your muscles and stuff, and you're trying to build up the musculature, but also you probably have suffered from lactic acid fermentation where you created acid in your legs, for instance, because you weren't delivering enough oxygen to those tissues to enable them to make ATP in an efficient manner by breaking down the food. So what people do is they do a lot of things in order to enable themselves to deliver oxygen better. So this is what I was arguing earlier. So you have people like cross-country runners, and what they do is they push themselves at practice every day. And what they're doing is they're pushing themselves, and they want to go right to the edge, but not do too much anaerobic, because if you do too much anaerobic, then you're unable to really perform very well. Have you ever seen someone running like in slow motion at the end of the race, or they just look like they're really struggling? that's inefficient breaking down of food right there, and that's not good for anyone. So what these individuals do is they push themselves to the edge, and a few things are going to happen. They're going to have hypertrophy, which means thickening of the left side of the heart, the musculature there, so it can beat blood more efficiently to the rest of the body. They're going to have an expansion of their lungs. They're going to infuse more bronchioles than the normal person will. So when they do it again the next time, breathe heavily, they'll have more respiratory exchange sites. They have increased rib cage musculature. The adrenal gland on top of the kidney secretes not only adrenaline, but also something called EPO or erythropoietin. And this is a hormone that goes into the bloodstream, specifically to the marrow of the long bones, and more red blood cells. Polycythemia is what it's called. More red blood cells are created, so the next time they can deliver more oxygen. And so the point is that they're pushing themselves to be able to do this better the next time. And that's why they're able to do, after a bunch of training, some crazy stuff. When you watch people running super fast for long distances, or someone going up Mount Everest, they don't just, I heard once, if you drop someone on the top of Mount Everest and they will die within 20 minutes because without supplemental oxygen, because they just don't have all these things, the red blood cells and all these increased red blood cells. So that's why when people go up Mount Everest, they go up, then they come down, and then they go up a little bit higher, and then they come down. They acclimatize over a period of time. But you can't tell these people that there isn't pain involved. Literally, that's why you see them sometimes like laying on their back with their legs up against a wall. So they're literally draining the lactic acid out of their muscles after a big work.
Walk along the razor's edge. Don't look down, just keep your head. Open up the limits. Past the point of no return. Reach the top, but still you gotta learn how to keep it.
Of course, there are other ways to do this. One way is to do similar to what the Nike-sponsored athletes do in Beaverton, Oregon. They have this literal house where they sleep every night at 13,000 feet. So all night long, their bodies are undergoing all this physiologic adaptation to the high altitude, and they're doing all this stuff that I just mentioned. But then they walk out at sea level, and then they go train all day. And that's what people want to do. You want to sleep high, but you want to have an efficient training where you train low. So someone like would train down in Salt Lake City, but they would live up in Park City. They would just live higher. Or you could do that. Well, this is how they did it with that house, is they hermetically seal it. And you could do this with a bed too. And I read an article about this guy once, and he said he was sleeping and he had an altimeter on his watch, and he wakes up and he can't breathe, and he realized that a cat like kicked a sock in front of the little air filter intake system, and he was like 27,000 feet, and he had a raging headache and everything. So he unzips the thing, and of course his eardrums hurt after that. And anyway, I don't think this would be a very comfortable way to sleep, but let's see what Dee Dee has to say about it.
The Cat 150 portable tent is the most versatile tent in our lineup. It's lightweight and compact and comes in a duffel bag this size. It's easy to set up, literally takes 15 minutes. It's designed to accommodate a queen-size bed. In fact, the mattress goes inside of the tent, and then the tent and mattress sit on top of the box springs. You enter the tent at the foot of the bed through a series of zippers. Once you're inside, there are several hanging loops so that you can hang a light or a fan in the tent with you. And there are access ports on both sides of the tent so that you can turn off your alarm clock or even get a drink without leaving the tent. Like all of our cat tents, it comfortably accommodates 2 people. Because it's so easy to set up and take down, it's the perfect travel accessory for the athlete on the go.
Yes, Christmas or whatever whatever holiday you celebrate, let's get one of these tents. There's another thing that occurs in nature. You can see that it's a little bit different here than lactic acid fermentation. This is the fermentation of pyruvate, and if you look down at the bottom left corner, alcohol or ethanol is made. Here's a character that does this. Yeast does this. You know, I'll tell you a story. My wife's brother in Ohio, Dan, he wanted to make some wine. So I'm not going to tell you how old he was, but he was not of legal drinking age. So he takes a bottle, he takes grapes, he puts some sugar in there, he puts some yeast in there, and puts some water in it. He wants to make wine, right? So he then corks it, he sticks it in his closet. He said for weeks, he would go back and the thing would like be, the solution would kind of move around every so often. And it was just this gross purple liquid, and it's fine. So he says one day he comes home from school and the house stinks. And he's like, oh my gosh, what's going on in here? So he's like, hello, is anyone home? And no one was home. So he walks into his room and his closet door was blown across the room on top of his bed, and everything was stained purple in the room. And now we know what happened. If you look here, one of the things that's released in alcoholic fermentation is carbon dioxide. And this is what gives beer its bubbles or champagne its bubbles, where they cork it before fermentation stops. So that's why it has super bunch of pressure. And what happened with him was he didn't understand that he needed to have a CO2 release valve somehow. And so what happened did happen. Could you imagine if we did alcoholic fermentation rather than lactic acid fermentation? I just think that this is kind of an interesting process. I don't know why it happens. I understand the evolutionary significance of lactic acid fermentation to literally stop the organism from doing something that's hurting it, but I don't understand the significance here. But anyway, it just has two steps. You can see here it's very similar to lactic acid fermentation, but CO2 is one more thing that's released, and then ethanol is made. With both of these, well, especially, I guess with lactic acid fermentation, what happens is when you're done running, your body will take that lactic acid and bring it up to the liver, and it will actually convert it back to pyruvate. But it takes some time, and then you can use that pyruvate to break down that pyruvate and make some ATP eventually. 9.6 basically talks about a few things, but one of the things it talks about is the utilization of other macromolecules for energy production rather than carbs. And you see carbs going right down the middle, and you're familiar with glycolysis and so on. But if you have proteins, like let's say some people don't eat carbohydrates and they just want their energy to come from proteins or come from fats, and you can see where the proteins kind of go into this process, and you can see where the fats go into this process. I'd like you to read the first 2 pages of 9.6 for sure. Well, if you were in class, this is what I would have you do. I would have you get a few pieces of paper out, and without looking at anything, no notes, no pictures, empty your head onto a piece of paper and write down everything you know about these 3 processes. Focus on the where, the why, the reactants and products. And the reason why I want you to do this is because it will then enable you to see how much you actually do know, which is probably a lot, and then where you need to study for the exam. So I'm going to ask you to show this to me somehow, either, I don't know if we're remote or not, either in class or take a picture of it or upload it or whatever. So I would say here is I guess a type of homework assignment or maybe in-class assignment. I don't know what this is going to look like. But the point is, do this. Please do this. Spend 10, 15 minutes doing this. And then I'd like to see it. And then, of course, I want you to keep it. But I would like to see it to know where you're at. And I want you to keep it so that it serves as a good summary for you when you begin to study. Thanks. We made it through Chapter 9. Thanks for your attention, everybody.